right, we've come so far since 14 weeks ago, when we were trying to figure out the philosophy behind free will and engineering dynamics. But here we are, it's the end of the semester, and goal is with module 5 to take some idea or concept from what we've been doing in the course and apply it to your own application. So module 1 brainstormed and you tried to figure out what was a good application of this class, but you've been through a lot since then, so now you probably have a better idea of what's possible, what a constraint really is, in terms of dynamics and kinematics. So now it's time to apply it your own way. And we've kind of done this 3 or 4 times already with the module quizzes, where we started off with just okay, what concepts did we learn? How do I demonstrate those concepts? How do I apply them? So it's kind of like you're building your own quiz, and you do the research to figure out okay, if there's a spring in a mass system, what kind of spring do I use? How is it connected? What is it actually representing? How do I take this idea that the world is an engineering mechanics system and actually show it as that's my system, this is how it works? What kind of impulse or momentum? Was there work done? Those kind of things. This is all very broad, big picture stuff. And there's probably a lot more specific questions for different applications and those kind of things. The form of the project, if any of the notebooks that we built together, it's oh, this is it. I want to use this and try to apply it somewhere else. I need these graphs, but for a different application. They're yours. You can use them however you want. So that's a great way to do the project, is try to get your ideas into a notebook and edit it and then submit that. Or it doesn't have to be that. All the homeworks and the quizzes were all handwritten kind of work. We did some graphing, especially in that first homework. But graphs are a great way to compare what's happening over time or compare 2 different systems. Or tables. We did that in that last module, just what happened? I changed mass. What's different? Let me keep track of those variables. And again, all that. I offer this every year or every semester, so twice a year. And no one has taken me up on it, but an interpretive dance final project would be incredible, of taking the mechanics of an engineering system and turning it into something that way. I think that would be really awesome. But it can be whatever you want. Reports, PowerPoints, whatever form kind of works for your idea or kind of where you're seeing this get applied. What questions are there so far about the project? Yeah.
So can it be submitted in a similar form to how the other projects were submitted?
Yeah. So if you're making a PowerPoint or a report, then those are kind of straightforward. Okay, here's the file that I worked on. If it's some other, if you're building a website or something, then maybe give us a link to it. This is how I compiled all the work. I want to use it as part of my engineering portfolio so that people know I'm the best. I know dynamics. Yeah.
I'm still doing that. We have to make up our own code for the
So if you're going to use Jupyter notebooks, you can make your own code. So there was someone here. He wanted to do a similar project to module 2, where we're looking at 4-bar linkage, but just a different version, looking at a piston cylinder. And there we had to change things a little bit. But I can help you edit code, or you can just send me hey, nothing works, and I can help get it working. But it's not required. It's not meant to be.
I'm just not sure how the project is supposed to work. It's going to look different for
every person will look different. Yeah, and that's totally fine. This is not like a push yourself to learn something new. It's you already did the work. You already know what's new. How do you apply it to something?
Okay, 'cause right now, like, I have it envisioned as like, I have my this model or something I want to describe.
Yeah.
So I just compile like these slides for something, anything of like the degrees of freedom and like equations of like freedom and stuff like that.
Yeah.
It's just stuff to explain its dynamics and stuff like that.
Yeah, and that would be great. Of kind of like, okay, here's the setup. Like I have X number of degrees of freedom. These are the forces acting on it, and the end result is like, here's my equation of motion. And with this equation of motion, now I know whatever. Like everything's a sine wave, or maybe it's like we've done a lot of this kind of work already. And if you're like, hey, I know I want to do something, like I want to plot this result, like I can help finish like the finishing touches there, if you want. Other questions? What other questions are there? Yeah.
How much of each, like, so you said like you learn a bunch of different things. How many of those like different things would you need in order to like get like a good grade? Is there like a limit on this?
This one, if you take anything from the class and you apply it, then that's worth an A.
Sounds good.
So this is the main goal for here is that like when you go out on an interview and someone's like, oh, I see you got an A in engineering dynamics. What did you learn? And you're like, stuff. Like then immediately they're like, okay, whatever. Maybe it was an easy class. They don't understand anything. But if the answer to that question is, well, I actually took a week of the semester and I started working on a 4-bar linkage system. I wanted to understand torque on the system and know like what kind of motor, like how do I choose a motor for this system? That's a much more like in-depth answer where it's showing like you actually thought about how is this engineering applied? Why do you do this kind of work? So that's the goal of this project is like take your foot off the gas of like cramming and studying and just try to figure out like why is this important? Is this part of your, do you want to do this forever? If not, that's okay. But if there's something like what kind of concepts do you want to like apply and use here? Yeah. Oh, like these are all like big, broad, big ideas, but in practice, it's like, well, write down some equations, get some numbers. It's like, that's what we've been doing. We already know how to do that. Other questions? Yeah, so you can push, like in terms of like how you want to do this, you can push yourself hard and try something new. And like if it doesn't work out, that's okay. But yeah, but it's worth like trying something. But if it's like, man, this class was a blur and I never want to see it again, take something, like apply it somehow, do a quick little project, and that's it. That's okay. That's all right too. It's a required class, so you're required to be here, and that's okay. Whether or not you want to be here or not, that's okay. You take what you get out what you put in. Cool. Can I check in on what people are thinking? Is that good? I like to start with note cards. That's how we started like each of the quizzes. But identify what kind of forces there are. Are there equations of motion that you're trying to get to? Rocket? Yeah. Okay. Yeah. Yeah. Because if you look up like rocket components, like a lot of it talks about what is the specific impulse, what is the impulse applied to the rest of the rocket. Okay. Yep. Yeah. Yeah, and there's a ton of different, like rocket science is complicated because there's so many different stages. Like each individual stage is not like super complicated, but going from one to the next, you have to like keep track of all the variables that happen during takeoff. That all affects what happens as you start to slingshot, which all affects what happens. So it's easier to take like, especially for this. All right, let me look at just one example. Either takeoff or some other stage, like whatever. Dragon is going to calculate what it means. Yeah. Yeah. Yeah, and there's like one thing you could think about is like what is the force of drag when you're like, let's say you're flying at a constant speed, but altitude is changing, so density is dropping, so you need less and less force as you're going up there. Yeah, so density would be a function of your altitude. Yeah. Ground level. By the time it's out there at zero, either way, I don't know.
As long as I have like that idea of where if I don't have that secret total amount of drag, it's ready to get off until it's spicy. I don't have that
yeah. And you'll have, like, if you know how fast you're going and your height, then you know how much drag there is. So then for every point you have a portion of drag is always that one half rho A B squared. CD is constant. Based on the shape. So A is cross-sectional area, CD is a non-dimensional shape, which is the coefficient of drag for shape. Like a sphere, I think is always yeah, that's got a CD. Yeah, yeah. Coefficient of drag. Yeah.
So I would
like in Wikipedia, there's a whole table for every different shape. What is CD?
So like if I looked up coefficient of drag for CD,
you can probably look it up for a rocket. There's probably sometimes it's lift to drag ratio.
I can just pick one.
Yeah. Okay. Yeah. Okay. So it could be like it could be kind of a reverse engineering question. And know this essentially works. What's happening? So identifying how stiff is the spring? How much damping force is there? That could be one way to go about it. Or another way is if this is the general sort of like, I have a mass and I have a spring and a damper preventing it from having too much bouncing the vibrations in the house. Imagine that there's some kind of force pushing on the reels. What does that force look like? A sine wave, a step function. So what happens to the rest of the text with A and B based on yeah.
Could we the
yes.
forward for this quiz like that we did? Could we use them to like help make our own
yeah. Yeah. Yeah, like all the quizzes were there was like we kind of identify like here's the problem, and then I go and do research to figure out like, all right, what kind of stiffness do we need, how much area does this thing have. It doesn't take a long time for time, but it takes work to figure out like what are the engineering things that are going into this problem to fill in details. And that's what
because especially like real estate, drag effects on like how long they are. It's like
yes.
So I'm getting that. Oh, so you know our projects
Okay.
and like send it in, how long do that? Do you have to just like email to the TA or?
No, just add a whole new submission. You can have unlimited submissions for.
How does that work? How will it
You can notify them and saying like, hey, there's a new submission. Did you already? And you're waiting?
No, we're about to.
And when it's like especially as the semester is like we'll go back. Hey, thanks for the comments. Making such progress. Awesome. Yeah.
It's gonna be
okay.
Background.
Have you seen like how yeah, if you want to take it in, try to come back, or we can talk about it.
I'm good. I can just. It's kind of like doing it all.
Yeah, it's kind of you. That's very good.
Yeah. I know one thing is because someone else was thinking about it. They were thinking like, if this is link 1, and then this is the connector link 2. This one is your link 3. Yeah. But what we found is like when you're swinging, really this one bends all the way up. We found if you start off with like just modeling a chip, then you can say like what do these arms need to guide this through that chip? Because otherwise you end up like like now you have
trying to code, and so I just put it in text box.
Yeah.
Just send it in the project.
it's like a little yeah. Your spin has two axes. Yeah. And then I know. Yeah. But the spin, it just like it ends up the same way that like velocity vector. I'm moving this way, but the river is pushing me that way, the total velocity that way. Spin is the same thing. I'm spinning in this axis, and rotating in this axis. My total spin is this plus yeah, because you can figure out like, all right, we've got some magnitude of spinning. It's a weird path of the now moving. I'm not just doing this, I'm like doing this. You'd end up with like a square. Still have R a squared. Yeah. Let me know if you're like hitting the wall. Yeah. Okay, yeah. One way is working your backwards. What does the head pretty good way to reverse engineer.
They can show you the picture of it on that. So they will show you the
So I'm thinking that I expand on where, like, I'm giving them like I'll make up a scenario where minimize the material maximize the efficiency. Okay. So I'm thinking like it'll have to give me a set of like, okay, like in terms of like a rocket that'll probably be and then I'm given like constraints on vehicles can only be like this long, how much we can get through. And these are like the massive you can put with like, yeah. And so I'm like,
The lower the mass, the better. I don't, that's a multi-people crisis on you feel that you get a pound, getting 1 pound of stuff.
So I'm thinking like, yeah, like make up like an imaginary scenario where let's say I'm trying to get supplies, let's say, and so that's our, it's like what, maybe 100 pounds of supplies, and then that has to be on the rock, and then
Pretty good.
Yeah.
I was trying to do, get up and move. I want to do shows, too.
Yeah.
I explain like exactly what it's yeah. But I want to do something like more practical. I want to really, I want to see if we can model something and actually try to recreate it in real life.
Okay.
I'll see this like, these things like football, right?
Yep.
It's like two goals, yeah, for football, spiral.
Okay.
And see if I can get like ECC, it's going to slow down and see how my model differs from how I see it.
Yeah. Actually, just trying to think of how I was like there might be a way to because like if you said you had and it was like a fixed things and then spiral smooth those kind of one line to stop.
No, there was like a different
Yeah.
First it another way. They'll go out and then back. They'll go back.
Yeah. Like,
Yeah.
but they
can figure out so we change.
Yeah, so
we could change something.
like alcohol during the beginning.
Now L starts to be you know how our curve the beta dot or halo goes down. It's that red dot.
I love how it's back That could work too. Yeah, something like that. I would like to model real life.
Yeah, it would be cool to just like see it, see it happen. Yeah. I don't have like oh, cool. Yeah. Cylinder. Yeah. Okay. Yeah, there's a student design project that's working on. It's not. It's more like unmanned underwater. So I don't know if it would be like an internal system or just like yeah, like I don't know. Yeah, at least some of like really fun. Yep. Yeah. You could look at like yeah, like submarine as a whole, now is that's it. How like the dot
This is sort of how his station.
Yeah, not exactly. I always had like a big part. Exactly.
Oh wait, no, I'm gonna make more accurate.
Yeah. Okay, yeah, those were. Do you know how to set up like the equation function? Okay, yeah, that would work. If you think about like when we were looking at the pendulum, like pendulums are kind of like the OG time similar to that. Now exactly. So like with those pendulums, there's design, at least like grandfather pendulum. It's a compound pendulum that has a frequency that is goes one resolution of 2 seconds. Yeah, so it clicks on both sides. 2 seconds. So you design it, it's like, okay, it needs to be this long, center of mass is here, like, okay, that's my actual frequency. And for that,
It's a similar idea for those like balance wheels. They kind of spin one way, stop and spin the other way. There, instead of having like gravity acting on it, a torsion spring. So torsion springs are measured as like Newton meter per radian. So as I increase the angle, it twists it back. Indoors, same thing. Like anytime you see springs, there's some torque for every radian that it increases. So that's like our input force, negative theta. And the measure that we have is the moment of inertia of our flywheel times the double. And for the most part, it's the same equation. We double dot into negative something theta. But now it's a flywheel. That would be like the starting point. Like how do I build a flywheel to a spring so that it bounces? I think it does the tracking wheels. Okay, alright. So that's the part that I wasn't sure about. Yeah.
So basically how, like, you know, depending on, like, you know, the change in the pitch of the blade as well, you know, how, like, you know, because when it's going to change the pitch or, you know, by certain, like, if you apply some amount of expansion, basically they're not going to be stable as they rotate, they're going to kind of flop around. So you need to have, like, these dampeners to kind of basically keep them alive and dampen those forces. The stability of the rotor, of the other blade on the rotor.
And the rotor wants
to twist, flap, shift, things like that.
So what is your free body diagram?
Honestly, traditional display of the different like sections, specifically the blade itself, the dampener, and like depending on like when you see one degree of motion of the blade that's going like here, flopping up and down like this angle, and maybe, you know, on the side. And then basically what the free body does with the dampener, you know, how you know, this motion affects you know, the pulling motion here in the dampener.
That you want to look at complements twisting.
Yeah, that's it. Like here, the bouncing kind of affects more like in this 2D, FPD, the motion of the, how much that plate is moved to the dampener. So I can focus specifically on that.
As it twists, pushes it forward. Yeah, that sounds cool. Waiting. No clue? Okay. So what was like our first, when we first started the class, like project one proposal that.
I was just looking up, you know, how it's
Okay. What would be,
I guess it's more materials. Yeah, the compressor blades.
compressor blades? Yeah.
It's more like a dual.
What would be, so if you could choose any material properties for those blades, what would be the best material properties?
Honestly, it'd probably be personally, we want to look at temperature. For the material, when we're doing the configuration of the templates,
Okay. Okay, yeah. High temperature, what do you want it to happen at? Because every material can be at a hot temperature. But what do you want to happen at a hot temperature?
Honestly, not break the floor, or basically,
What is breaking?
so basically, the thing is, I've noticed, I watch two accident videos.
Yeah.
And generally, it's, a lot of issues are on the workers' part, but sometimes it's like, you use an engine for so long, that the blades actually start to bad. And then there are these little micro graphics in the families. And sometimes those families break apart.
Yep.
Upon use of light, and sometimes you can do an install. Well, not an install, probably do a compressor. And in most cases, it's fine, but there's a good
Right.
Just towards.
So
I know, there was this incident, there was like this, turbo bus. There was a piece that,
yeah.
and the whole engine was basically, actually two engines. And they have to, they were in Alaska. I don't remember the exact. So something with like, maybe like a simulation, maybe for, I know there's something already out there, something more simple. That could like,
So in terms of like, and this is, it's a real ongoing problem, like, design. Like, we're always trying to push the material properties, but you have to choose what material properties you want to push. That's why I have to,
I wanna try to push temperature. Like, I know most materials can't handle cold, like,
what about
like, we want a higher limit. Because sometimes you
then why
might,
not use, tension or ceramic mud?
I mean, it is possible,
Yeah.
but,
Why aren't, ceramic matrix composite steel?
it's very possible, but at the same time, mass is also a big issue.
What was the first thing that you said about, like, how did it fail?
Little cracks, yeah, the
What
worm.
happens in a crack?
The fatigue,
Yeah,
yeah.
what's the fatigue like of a ceramic mud? If you have a small crack in ceramic mud, how long is it gonna last?
I actually don't know.
Like, yeah.
But I get the idea.
Yeah. So we're, like, the idea is like, we want reliable is like at a high temperature.
At a higher, like, it's a higher temperature. Or reduce fatigue, not exactly, yes, right. Even with the materials we have carbon fiber, still have fatigue, tank and still have fatigue.
Yeah.
So part of it
I mean, steel doesn't grow in those conditions. There's a
is, as much, but it's too heavy.
Steel has a fatigue which is lactic about steel. You don't believe me?
No, I do, I have that same note, damn.
Okay, alright. It has a limit, like it'll last forever until it rusts, but that's it. Like we could build this full engine out of steel, it's just run at a full temperature.
That's challenging.
Yeah.
I've seen how Russian aircraft, they built their compressors for the engines using materials on insulation, they would heat up very easily and just, it go into the.
So at least from the dynamics thing about why are these things failing, it's like they're spinning at a certain speed.
They're wear, yeah, so why are they wearing on fire?
Yeah, so if you're moving at a certain speed and you have a mass, now you've got F equals MA, so you'll always, right, so you always have that centrifugal force trying to pull your blade apart. So that's the first question, is like, what is the load load on these plates. And then from there, you can start to say, all right, if the load is always this, temperature is always that, where in my material space can handle high load, high temperature.
Now, my
Then start narrowing down.
it's like, that makes sense, but at the same time, knowing how, violence usually is going to be consistent, so that's also a big issue, it's not gonna be consistently pushed all the way
But for the most part, high throttle is high there's
So maybe rather than,
there's jerk, but you can calculate like if you're going from one speed to another, what was the input supply change momentum? It's going to be a lot smaller than centrifugal force pulling it away.
I was also thinking, rather than, doing when throttle all the way, why not, see what happens, just like compress each adds that height.
Yep.
Well, not exactly idle, it's like, it's past the takeoff thrust point, it's in flight.
Yeah.
And maybe I use,
Cruising.
yeah, cruise,
Yeah.
and then I see how do these manufacturers?
Yeah.
Airbus is fly by wire, Boeing is a little more manual.
Yeah, that would be good.
So you pull if there was
Yeah. Well, we're working on Oh, okay.
Yeah, so basically, I want to do something with the power, I just don't know.
Yeah. Okay.
Like the engine. Power plant.
Oh, okay. How is friction from the ground?
Well, I kind of have an idea.
I mean, you have a spring, you have this needle valve, and then you have basically the fluid that works as
Oh, like
you can focus on the mechanical aspect of the injector, for example,
a resistance to the train. Like the fact that your wheel straightens out when you let go of it? Just have friction. I'm just trying to think. I'm not asking you, I'm just like,
Okay.
now I'm really thinking about it. Yeah, the car is but that one I think is due to like jamming your hand down.
I mean, if I can.
To reduce the moment created, but I think the reason that it straightens out is due to the dynamics of the car.
I'm just trying to think.
I think
Fuel injectors are way to go.
there might be suspension setup like depending on camber too.
Okay, maybe not the
Straight
pressure
out.
per se, but like,
Because you could set up a car that does not straighten out, right?
Or you can model out the vibrations of the compressor. You can search for what computer confused to,
so basically what you're saying about the
yes,
law.
that's what Paul wants to not the vibrations.
Because like if you're sitting still, like even if you park on the ice,
Maybe there
you
is,
turn the wheel,
there
There
is
is
it
something.
just sits there,
dampening or balancing.
even if there's no resistance.
Well,
But then when you hit the gas and you start moving forward, the wheel immediately tries to turn backtrack. And I think that has to do with like, one way to kind of think about it is like,
my other option.
how much force does it take to go this way versus go straight? So at a constant speed, there's 0 force to go straight. But if you're turning, you need F equals mv squared for r, whatever the turning radius is. And your system wants to go to 0 force, so it's gonna try to get you back to a 0 radius. Back to non-zero radius. I think that's part of that. Could be wrong. It's not the first time you've been wrong. But yeah, I think that might tell you. Or you can force that you need probably
Your
about
father has one of those.
whatever turning radius you need.
Your grandpa has those big.
Based on just how the car needs to move around.
He does, not the longer, but he does have like.
you need
Either
more
like check
force.
valves, like fuel check valves.
The bigger the
or
radius,
just
the
like
less force
fuel.
because it's one
I don't know
bar.
what's the schematics, but
Yeah.
these like, these valves.
Yeah, like
systems,
square root
just
R, so like
fuel,
if you want a
a
really tight radius and really high speed, you need to apply some force to like yank it over to get that wheel.
It's a hydraulic schematic.
I know the training manual
I was
provide
thinking
some
something
useful
like
radius
penthouse.
Nice, yeah.
I didn't know that.
But let's be real.
I don't know if that's the size of spillways that like measure earthquakes.
Yeah.
Like how they are So I was-
Oh, is that how they work?
Yeah, I
They use
was
a
thinking
pendulum?
yeah, I was thinking it to use
As you
it.
rep.
So I was thinking about
Also,
Yeah.
we weren't too
I don't
excited.
have them. They're
Okay.
all the way there.
Yeah, or like what happens to a pendulum if you shake it? Have you ever seen Yeah, I would imagine that that's what that one's doing, is to track the angle as this thing is moving. Yeah, that would be good. Now it's kind of like you have a pendulum pivot, you go left and right.
What I was thinking,
Should be
right, power plant.
the left, right, these are.
Yeah, so I was thinking like a PowerPoint.
Why not like
That would work, yeah. Cool.
basically what I
So you
do
have like
earthquake.
No, I was just that part.
It is interesting.
Yeah.
Yeah.
I love it.
Years ago, I stuck with me forever. Yeah. Hit by a radioactive earthquake. Okay.
It was like
Do you want to look at changing mass?
So I got this breaking arm, which is.
Rather, I was thinking.
Mass is based on time. But that's then I played based on this.
Yeah, all right. Yeah. Okay, that sounds cool.
I don't know.
Not in our thing, but.
We already have.
But same equation that you just did, right? The only difference is that C is constant. But if you want to look at
I remember at the beginning, the first project, I talked about
Yeah.
tried that for like, probably took a paper.
Yeah, that would be cool. Okay. Did you find?
Yeah, I mean, I was simplify.
The one that I really like is Miranda.
Look up her.
It's not a bad idea to say what you know right now.
But there's one, she goes, she has like 4 notebooks walking. It's a simplified version of like fluid, motion, and then like stepping it through. If you want to do like numerical computation, I want to look at what the path is.
Yeah, I was thinking of trying to code so I could like graph the motion of it
Yeah,
to count
yep.
like oscillations.
Yep. Yeah. 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 So you end up with like 2 design, like a 2 degree scale.
Yeah.
Height and pitch. Or she walks through like how to set up those 2.
I mean, this might not be too
differential.
This
This
might be
one
too
is to watch.
The clutch mechanism on
pretty good. So I have like my guy.
Yeah.
How should I do
You
it?
can explain it to
Should I
me,
kind of
you
keep it
might.
like together? Unless I'm focusing.
What do you think?
But at like the point that's
So depends on what kind of motion.
I guess one thing like this.
Literally
I'm
every
trying to
time
find
I sat down, I was just waiting for him.
how much it can try to
Get an email saying, yeah.
So I tried to explain
Kind of going from
Yeah, you already have a step. Why is he sending it
You shot one with a price of like 88 or something.
clutch. So it's like so much involved. Like it's like there's so much of this involved in its components.
Like now I've got 2 degrees of freedom, like the bouncing left or right and bouncing up or down. And depending on what you want to know, this one will tell you like this one will tell you like what should K1 plus K2 equal. This one will tell you like how far apart they should be mounted, right? Because if you put them both in the center, you're never going to stop.
The clutch.
But if you put them all the way out of the edge, maybe there's too much damping. But it would tell you like how much more you kind of rotate on it. Yeah. So this one's like more work, and now you have 2 equations of motion for both of the moments.
I am doing like just like the one side.
Yeah, and even if you only consider like one side, like if you're saying like this one is constant, you still have like angle. I guess like angle and x are both related to each other now. If you're saying like up and down, what's happening? So you have like this problem of one constraint. Yeah. Or like x, because then x will always be equal to like L to beta, but choose up and down.
Right.
Yeah.
So this is my integral that it's a warp and drag from the sea level to 10 million meters in the sky.
Okay.
It's this is the equation of drag, but it varies. It's a function of altitude.
Okay.
So
Yep.
the thing is, I'm going to assume that velocity is constant, even though it's not. But for the fractionality of the problem, I'm going to assume the velocity is constant.
Yeah. Yeah, that's okay.
How would I
Me too.
How would I integrate something with
What's the second?
velocity doesn't matter. So one velocity would be a function of time. So
Well, if it's a function of time,
and this
h
one
is a function of time.
H is a function of time.
Yeah, so H is time and,
I'll replace this H in function of time.
yeah. So, like,
Honestly, I'm just gonna do like a very basic analysis, like
think about it this way.
flight controls,
Um,
so fly by wire is the best, technically. If you want to trust
T, let's say we ramp V and T, so it started at 0.
It does apply, it does
It goes
apply.
up. Now,
Systems,
H.
manipulate physical components.
And T starts at 0. Yeah, so there's always a relation.
No, there
At least
is,
if we're just thinking about like this
it's
straight
the
up.
way they set up.
I mean, if we're also saying
So obviously, fly by wire.
it's straight up, there's gotta be
The way they set up
V
the systems on there.
constant acceleration, H is a parabola,
There is a difference.
V is like
One,
some other function, and H is the integral of V.
the other one.
So everything ends up being like just a function of time.
It doesn't matter which one, so.
It's not to say that you can't do double integrals, you can't, but
Because they're
Maybe
more
like,
error.
like that was what I was thinking about, something that's not.
I was thinking like, you know,
But like,
when I got level wires.
But here we have, because our definitions are always that V and position are always connected, then at the end of the day, everything turns into like integrals, really time. Here, work is an integral over distance.
So I would have to, if I did change this, if I did change the problem to make it more complicated, it's functions. It's also functions. This
Applause is like index B, like matrices.
So if you integrate like,
Just applause.
if you integrate force over time, you end up with impulse. And then force over distance is gonna be,
Yeah, I guess it's not that bad.
an integral dx is work, integral dt is
Shoot, yes, we have no quizzes. So right now, this is,
You don't have that.
well, I get, if this, so if V goes like that, H goes like this, then I can combine the two, right? V as a function of H is still,
Oh, Jackson. I thought you had this.
so if I did do this out, would I really solve the code?
Here's the best option I
it
have.
would still be work. Yeah, as long as you say integral of force over
Yeah,
x.
it's really good.
Yeah,
Okay, so that if I change this to force over time, it's not.
now it's impulse, total impulse created to do this, to get up there.
I'll be solving something else.
Yeah, then you would, well, like if it's a function of time and H is a function of time, you can always say it's a function of H. Yeah. But yeah, you can always change variables, because if you know H is a function of time and everything is a function of time, you can say everything is a function of time.
So I can make a velocity.
Yeah. You might end up with like a pretty nasty integral, so it might be worth like plotting it and then do numerical, just sum all the dx times the value. Yeah.
As long as that's me, I appreciate it.
Yeah, thanks. You too. Sure, yeah. Yes, yeah. Okay. Right. Sorry about that.